So welcome to our Statistical Mechanics Lecture 3. So this lecture is a physical example that is going to help us to see how we connect from the microcanonical ensemble into the canonical ensemble. So to remind you of the microcanonical ensemble, these are the key equations that we need to know to use it. So in the microcanonical ensemble, we need to be able to calculate the statistical weight. And to calculate the statistical weight, we have this formula for counting little n objects from a total of big N objects. So we can use that to assign the statistical weight. We can also use Stirling's formula to get rid of all of these factorials, which are very difficult to manipulate algebraically. And you will notice conveniently that the Boltzmann entropy, which takes the log of the statistical weight, brings these logs in. So we can do that very conveniently, as we're going to see in our example. So let's go from the microcanonical ensemble into the canonical ensemble using a physical example to take us there. And the example that we're going to use is called the Schottky defect. So let's just chat a little bit about what this system is. So imagine that what we have is we have a crystal, and that crystal, of course, isn't infinite. It has a surface. Now, if we imagine our system at 0 Kelvin, what is happening? Well, of course, we can't get to 0 Kelvin, as we'll see when we discuss the third law. But imagine that we could, then imagine what would be happening. And of course, absolutely nothing will be happening at all. That's the thing about 0K is there's no motion, there's no entropy, there's nothing. Everything is completely still. So, okay, so if we forget about 0K for now, because we can't get there, and we start to heat our system up a little bit, then what's going to happen is our little atoms or molecules, our particles, are going to start to wobble around their equilibrium positions. And eventually, as we get hotter and hotter and hotter, some of our atoms or molecules are going to have enough energy that they vibrate sufficiently that they can actually jump out of the lattice, and then they'll sit on the top of the surface. And that's what's called a Schottky defect. It's when we have a hole left in our lattice because some of our atoms or molecules have attained sufficient thermal energy to be able to escape from the crystal. And of course, this leaves a vacancy. Okay, so now we can actually try and calculate how many of these vacancies there are as a function of temperature. So the first thing we have to do is we have to write down the energy associated with one of these defects. And we do that very straightforwardly. We say that the energy associated with little n of them, of our defects, we assume that each defect has energy epsilon. So the energy of n Schottky defects is little n times little epsilon. So E equals NE. So we've written down the energy of our system, and we're in the microcanonical ensemble. So remember, the energy is fixed. So we're not considering the system in contact with a heat bath. The energy is fixed. So we can also write down the statistical weight, because we have our formula for how to pick little n objects from big N objects. And what we're doing with our defects is we're creating little n defects from a perfect crystal that contains big N atoms. So straight away, we can write down the formula for the statistical weight associated with little n Schottky defects in a crystal containing big N atoms or molecules or particles of some type. Okay, now we've got the statistical weight. Of course, we can calculate the entropy using Boltzmann's formula. So here we go. So we can write down the entropy. The entropy associated with little n Schottky defects is the K, Boltzmann's constant, times the log of the statistical weight associated with these little defects. And we can write that down here. Now, you'll notice that we've got all of these horrible factorial expressions in here. So we're going to want to get rid of those using Stirling's formula. So I'm going to do that now on the document CAM. So we have our entropy as S of little n equal to K log n factorial over okay. So let's start off by just calculating this expression. So let's take ln of big N factorial okay, so let's take this expression and use Stirling's formula. So ln n factorial equals n ln n minus n. And let's simplify this. So first of all, we want to split up all of the parts in the fraction. And we can do that because of the amazing power of logs. So logs are ace. So if we take this expression here, so we have ln big N factorial, then we've got minus ln n factorial minus ln little n factorial. Okay, so now we want to apply Stirling's formula. So we've got this all in a line. So of course the things on the bottom are just minus because of the rules of logs. Now we can use Stirling's formula. So we want to do this term first. So ln of n factorial. If we look at this is Stirling. Okay, so if we look at our Stirling's formula, we can multiply these out term by term, and we've got to be very careful of the minus signs. So we have ln n factorial is big N ln big N minus big N. Now this one, let's not worry about the minus sign. Let's put it in a bracket. So we have big N minus little n ln big N minus little n minus big N minus little n. Okay, so that's that term. And now we want to do as well minus, so let's put that in a bracket just to keep our life easy, little n ln little n factorial, n ln n minus n is little n factorial. Okay, right, now, so let's try and multiply out all of these minus signs. We've got n, ln, n, minus little n. So that's going to be minus this, minus n minus n, ln n minus n. So now this is minus, which is plus, that's minus, which is plus n. So this must be minus little n. And then this must be minus n ln n. So that must be plus n. Okay, so now you can see that loads of things cancel out. So we end up with n ln n minus n minus n minus little n ln m minus little n. So now this these two things cancel out. So I needn't have written that one there. And this one and this one cancel out. So I end up with minus n ln n. So let's just write that out again. We've got n ln n minus and that is our simplified expression that we need to now substitute in to our entropy. So our entropy, S of omega of little n, is equal to K n ln n There we go. So here is our expression for our entropy. So S of little n is this expression here that we've just arrived. Okay, now what do we do next? Now we want to calculate the temperature. And we can do that using a little expression from thermodynamics that ds by dt, ds by de is 1 over t. And I'm going to convince you of that now.